So we have been looking at branching, okay, and we saw actually quite some non-trivial branching, okay. So what we saw yesterday was the following set of branching. Right? So we did customary vertex cover, like just in case. I mean, you would have forgotten. So like, I had to remind people that there is something called vertex cover, and we have to branch. Okay. And then we did feedback vertex set based on alpha covering log n power k log k power k. क्या प्रोबेबिलिटी है कि संयुक्ता लेट आएगी? 1. Okay, and then we saw some more example. I think we saw some more. Okay, so we saw 4 power k for max lift spanning tree. And I asked you as an exercise, look, I'm not going to ask you for homework, like please give me. It's for your own sake. Like, it's easier to understand something when you just like run through on a different example. Oh, this is a direction, and okay, for max lift spanning tree. And then we did a dominating set on D-degenerate graph. What else did we saw? We saw one more example. Closure string. This is what I forgot yesterday when I was sending my email. See, we saw closure string. Two things. Closure string. We saw d power d algorithm, and we saw 1 over epsilon to the power d 1 plus epsilon approximation. Am I right? This is what we saw. Yes. Battery is low.
No, this wire is hanging. It makes some noise.
Okay. Just put them. Okay. Okay. So I will do two things today for branching. Okay. Since people want to do this K minus LP business, I will do K minus LP business. But we do SVD, split vertex relation. And then we will do above guarantee vertex cover. And then, okay. And then we'll move on to a different set of things. Okay. So let's do SBD. Okay. So what was the split vertex relation algorithm? Input is G comma K. Okay, and question is, that G has a set of K vertices whose deletion so मैं क्लास में हूँ, बोलो मेरे बैग के अंदर देखो, हो सकता है उस रूम में बैग दिखा कि मेरा काला वाला, तो उसको Did he say something?
He adjusted the AC.
Yeah, it was too much. Okay, whose deletion leaves a split graph. So clearly, all of you told me that it has a characterization as excludes induced C4, C5, 2K2. Okay, here's a very long time back I saw or proved, I really don't know. So this definitely gives you how much? 5 power k algorithm. Do you agree? Right? Because I will find one of them. But you can show this is a nice graph theory result. This is a exercise. Let G be a graph that do not contain, that doesn't contain induced C4 and 2K2, then it has unique C5. So if I prove this lemma, suppose, then what algorithm will I get? Right? So first I will get rid of C4 and 2K2, which are like 4 obstruction set of size 4, and then graph is so simple that I can solve my problem in poly time. So 4 power k, excellent. Agreed? Right? But you have to prove this lemma. I mean, this is. I mean, then it has at most. You start proving, you will get where. I mean, this is just out of my memory. There was no hot water, so I'm drinking cold tea. Anyway, fine. Okay, but that is not what I want to prove. Okay, what I want to show to you is something more funkiness. Suppose I given a graph G, I gave you a partition of vertex sets. What did I give you? Partition of vertex. Look, after I delete this k vertices, right? Suppose this is my split vertex solution. After I delete, what am I going to get? I'm going to get a split graph. How is that split graph going to look like? Right? This is click and this is independent set. Right? So let's call this C and let's call this I.
Then already have like a graph that does not contain induced C4 and 2K2. But if I take root to disjoint C5, then do you need more conditions to there? You directly get something, one of the obstructions. You'll immediately get 2K2.
Now what she says that what happens if maybe I need connectedness.
No, you get 2K2. No, pick an edge from here.
Here and pick an edge from here. Haha. Ha ha.
But then you'll probably get C4.
Yeah. I remember proving this. It could just well be wrong. Maybe I made a wrong proof, but that's your. I think something of this nature is correct. Like I remember that this is how I made my first 4 power k algorithm for split vertexation, and then I realized that there are like trivial ways to improving it, like 2 power k. I didn't know what I will teach you. I didn't know, but I knew how to do 2 power k. But first, like after a lot of hard work, this is all that I got. So I thought at least graph theoretically this is an interesting result. No, that if I exclude these 2 objects, right, then induced C5 has a very nice structure. So if you're interested in graph theory, it's a good graph theory exercise, right? And this is not any book or something. I mean, you can prove it from the basic set of tools and trying to play around with it if you really like graph theory. I mean, it doesn't require some heavy machinery or nothing. It's like just basic set of things, okay? But it's a fun lemma, right, to remember. Okay, anyway, so she's right. You're excellent. And I was just like, thought maybe I need some connectivity. And no. Saved. Okay. So now suppose I have C and A, and I Like I do not know where this C and A is, but for graph, and if people who know this answer, okay, suppose given a graph G, I gave you a partition A, B, okay, I gave you a partition A and B, and I told you promise, and what is a promise? Here's a promise. C is subset of A, I is subset of B. Suppose I gave you such a partition of my graph. You understand my point? I want to solve a split vertex solution, okay? And suppose I know that if after I delete this S, I will get a partition of my remaining vertices set in C and I. All I'm telling you, I'm giving you a graph G and I'm giving you partition of G into A and B. And I'm additionally promising you that look, I don't know what your solution is, but the click guy which you will get after deleting your solution is actually here. And that independent set guy which you might be getting after deleting your split guy is here. Then can we solve this problem? Like I promise, so suppose this is a promised version of split vertex solution, then how fast can we solve? What do we need to do then? Do you get my question? Right? So I've given you a graph G, I have given you a partition of the vertex set, and I have promised to you that that after you delete like this imaginary C and I guarantee you C is in A, I is in B. I guarantee you that. Can you use this fact?
So here, if you find a minimum vertex cover,
Have you seen this before? If you have seen this before, then there's no point, right? Then let other think.
Vertex cover will intersect with the cover of the edges and whatever subset we need.
So Kanya, you can be louder. Why are you afraid? In the worst case, you will make a mistake. So what? So you can be a bit more louder so that others can also hear.
Yeah, so I was thinking since we need an independent set in B,
Yes.
we'd probably look for a vertex cover, minimum vertex cover that would be covering at least all the edges of that subset.
Okay. So what you are proposing, okay, is that let us find minimum vertex cover in graph induced on B. Am I right? Okay, fine. Okay. Suppose I find a minimum vertex cover. Let's call it S vertex cover. What else should I do? And what do I need to find there? Huh?
You wanted a click in it.
Okay, so let's write. So what you want to find?
Max click in it.
Okay. So max click. What is max click in this graph? Can I reduce? If do you know an algorithm to? So basically, what we want to find, let's say, minimum number of vertices such that minimum number of vertices, say SC, right? Such that graph induced on A minus SC is a click. Am I right? That gives you disjoint union of click. I mean, that algorithm will give you because it's 3 power k, so I branch.
Need just one click, right?
So, like one of the branches will have just one click. Okay, think about it. I said something more. Right? Because I will output all possible cluster graphs up to this. But it is more easier. Complement graph. So what I could do, I could say same, find minimum vertex cover in G bar A. and then I'm done, right? So like if I'm looking for k-sized split vertex solution, I can guess, oh, k1 from left side, k2 from the right side, and apply the vertex cover algorithm on the left side, right side, and I'm done. Because once I find this, I have a click and I have an independent set, right? And whatever left is split graph. I don't care about the edge cross between them, right? So if someone gives me this partition, right? If someone gives me a promise partition, then I can solve this problem in the running time proportional to vertex cover, right? Because what is it? Suppose vertex cover has running time alpha, then this is going to be alpha k1 times alpha k2, which is alpha k, where alpha is the running time of vertex cover. Because I have divided my solution also. It's not that alpha k times alpha k. No, I want k1 from here, k2 from here, and k1 plus k2 is at most k. So this is, I can get a split vertex solution algorithm in discover time if you give me such a promise. Okay. So now our question boils down to finding this promise. Okay. So now we will try to find this promise. Okay. Unfortunately, we cannot find one promise. Okay. So what I'm going to prove to you slightly so here is what I'm going to introduce, what I call separating families. Okay, so they are called, the objects are called separating families. I know there are people in this room who has made their lives out of separating families. So this is called separating families. So what is a separating family? I'll give you an algorithm. Given a graph G, we will find a family curly P of partitions of Vg into some AI Bi. Okay. So what is P? Is basically some A1 B1, AT BT, okay, right, into AI Bi, such that what happens? Given any C comma I, where first C intersection I is empty set, C is a clique, given any C comma I of G, C intersection C is a clique, I is an independent set. Who is attending communication complexity course? You have seen this before there then. It just comes from there. Okay? And its complexity was settled completely only a couple of years back. Okay, I'll tell you a story a little bit later. So okay, where C intersection is phi, C is a clique, I is an independent set, and such that given any this, where this we can find some Aj Bj in P such that C is subset of Aj, I is subset of Bj, and T is upper bounded by n to the power big O of log n. Okay, so what I'm saying to you, given a graph G in n to the power big O of log n time, I can come up with a partition A1, B1, A2, some family of partition with the property, you give me a clique and independent, your choice. I don't, but only thing is that this C and I shouldn't intersect. They might intersect a single vertex, but I want that C and I shouldn't intersect at all. Then I will give you AI Bi in your family such that C is contained inside AI and I is contained inside Bi. Okay. Suppose if I prove this lemma, then my running time of my algorithm will be what? I go through each such partition. I know that C and I, after deleting split vertex solution, is I take that C and I apply this lemma. So there is a partition where this is properly done. Agreed? Get my point? So look, this doesn't, it says given any clique and independent set whose intersection is non-empty, I will give you a partition AI Bi where C is this and this. So now I don't know this C and I, but I know for sure that there is some partition that contains this C and this I by the property of the family, separating family. So what is my running time of the algorithm? If I give you this algorithm, you go through each partition, and for each of them, you check that does there exist a split vertex deletion like this. So the running time of this algorithm will be how much? Alpha power k times n to the power big of log n. Okay, so this is not FPT. So what should we do to get it FPT? I mean, I can tell you lots of hacks, but I can tell you lots of hacks. Okay, let me tell you one hack, but this is a bad hack. Okay, how to get this as a function of k? So what I probably could do, let's think. I may be completely wrong. Think. Okay, so I apply some factor approximation. Okay, so I will get some 5k solution for split vertex deletion. I have a clique and I have an independent set. On this, I apply this lemma. On this, I apply this lemma. On graph induced on this, I'll get some partition, right? I'll get some partition, right? But how many such partition will be there? K power big O of log k. So I take each partition and then I'll create more partition. I say, look at this clique guy. Look at this clique guy. I mean, look at your optimum solution. From this clique guy, either he will delete some vertex or he will keep the way it is, right? So what I will do, I will add the whole clique guy here, except one vertex, because that may move to independent set. So for all choices of clique, one vertex, I decide which vertex will move, right? And then I can put some C prime, I prime here. Okay, how many such things I would have created? At most, some n square, right? Now I can apply my algorithm and I will be done. This is a hack number 1. Okay, but this is not a good hack. This is applied in the case when things are very, very bad. Okay, this hack is discovered for something very unpleasant things, but there are much more pleasant way of doing, and I want to understand that you people understand. I do not want to apply this hack. So what will I do? Check for yourself that you could do play around this and you can get a family of size k to the power big of log k n square, and then you can try this, and this is FPT, right? But I do not want to apply this hack to this problem. It's too easy to apply such kind of hack. Okay. Does split vertex deletion has a kernel, polynomial kernel? You don't know? You know actually. Do you know a kernel for split vertex deletion? No. Do you know kernel for split vertex deletion? 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 Do you know kernel for do you know? Do you know Pratibha? No. Do you know Abhinandan? Do you know lock-in? Do you know kernel for split vertex deletion? Abhishek, I will not ask you. My God. Okay, just think. Actually, I taught you. I taught you kernel for any problem which has some properties. Okay. If everything needs to be explicitly told, then let me tell you explicitly. let F be a family of graph H1, H2, HL, okay, and max of HI, I going from 1 to L, it's a beta, okay, beta. And my question is F something 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 vertex solution, and objective is to delete k vertex such that no graph in F is an induced subgraph. Okay, no graph in F is an induced subgraph. That's my objective. Okay, so now what I do, I look at a graph G, okay, and I make a family F. Okay, for example, if I wanted to do a split vertex solution, what I will do, I will look at the graph G and I will make a list of induced C4s, C5s, 2K2. What is this? Yeah, I'm not talking about 5 hitting set and 5 power K algorithm. This much I know. So I apply kernel for a 5 hitting set. But wait. So I get some F prime such that the number of sets is bounded by K power 5 roughly. Right? Is that a kernel? All I know that there exists a solution here, but does that mean that it is a kernel? Do you get my point? Look, I reduced this problem to some family problem. I got a kernel for 5 hitting set. That doesn't imply that that's a kernel for this. But I also taught you a kernel where F prime was subset of F. Right? I also taught you a kernel where F prime was subset of F. Okay? Now notice, look at the number of vertices which are involved in this F prime. Right? It will be something like K power D times D. Now look at the graph induced on this, right? Notice, because I have taken it might have more induced subgraph, but it definitely contains all induced subgraphs that is contained inside F prime, because it's an induced subgraph on these set of vertices. So it contains all the obstacles which are there in F prime. Now you can show that this is a kernel for this particular problem. Okay, and so if any problem which has finite forbidden induced subgraph admits a kernel by this way. Okay, so we know a kernel of size K power 5. So what will I do? I will first get a kernel and then apply this algorithm, right? Then immediately I will get what is n is K power 5 and what is log n K power 5, so K power log K, right? So if a problem admits a kernel, I could first apply kernelization and then apply this lemma on the kernelization. Right, and I can get. Or if my problem does not admit a kernel, then at some time we can find a hack using some approximation solution, doing something, and maybe the number of ways I have to move things around is polynomial, so I can get around it. For example, for planar vertex solution, I do not know how to get a kernel, but I can do some playing around like this and get such kind of things, which is useful for FPT settings. Okay, good. So now we all are here. Just boils down to doing this thing, right? Proving this lemma. Hopefully I can prove. Let's see. All good? So now you know kernel for almost every problem. Look, these are very quick comments, but you should go and check yourself that these things do work. Like you should prove equivalence and everything. I mean, if you are not able to see it now, it's very important that you go and check these things out. Okay. So now let's try to prove this lemma. So what will we have? So we will have some sort of state at any point of time. Okay. So this guy will procedure. So there will be a procedure. I'll tell you, write down. which will generate this partition. So generate will take, okay, generate will take two things, three things actually, a graph G, a number D, and a state delta. Okay, so what is a state delta? Let's try to understand what is this state delta will be. So this state delta will contain partition of my vertex set. Okay, so it will contain, let me use the notation which, okay fine. So it will contain VC0, VI0 and A. So what is the meaning of this? The state will mean, look, I have already decided some vertices to be put inside VC0. I have already decided to put some vertices in a partition which will roughly correspond to independent set, and there are set of vertices which are still active and we have not made any decision whether they will go to towards click or partition toward independent set. So this is, so in the beginning, what is my state on which I will call my algorithm? I will call my algorithm, I will fix this D later. I will call my algorithm on delta, which state will be empty set and VG, because I have not made any decision about anybody, right? So this is all. Now given a state, how will I go about? So it's a branching algorithm, right? So at this point of time, there could be two things. The click and independent set which I am hoping to achieve, already the click which I am hoping to achieve is already here, and and so suppose I have some click in my head and independent set in my head. By God grace, C is already a subset of VC0 and I intersection VC0 is empty. I don't know this, but this could happen, right? So at this point of time, it's good that, okay, let me generate one partition which is VC0 union A, VI0, right? So this is a partition I can output. Or it could be that already the I which I have in my head is contained inside VI0, okay, and C intersection VI0 is empty. So then at that says I should output.
First one, do you want to put A on the independent set side?
Okay, that was my mistake. Sorry, it should be this, right? And here union A, VI0. Okay, so at any point of time I said, oh, I really do not know. Maybe I should make some decision. Maybe I already am done. So let me output this, right? So this is our. So at any point of time I say, hey, take this. This could be your potential partition. Okay, so put this into a family of partition. Okay. And then I will try to handle, maybe this is not yet done, so I have to really do something active on active vertices. So I'll tell you how to go about it. Okay?
So can you please repeat this?
What?
This.
Look, I have currently some state, right? But maybe for some click and independent set, click is completely contained inside VC0. Click is completely contained inside VC0, and the independent set which you have in your head, whose intersection with VC0 is empty. Now, how do I handle such click and independent set partition? I can handle such click and independent set partition by keeping VC0 the way it is and moving A to VI0. So this is one, so in my partition of AIBI, this is one particular partition. Now, what is it handling? It is handling that C is completely contained inside this, and I was promised that independent set is not here. So independent set vertices which you have in your head either belongs here or belongs to A, so I have put them together. Now symmetrically, it could be that the I which I have in my head is completely contained inside VI0, and C, the click which I have in my head, is not in VI0. Then to take care of such partitions of click and independent set, what I could do, I could move A to VC0 because that is where all the clicks are, and independent set which I had in my head is already here. So I will output this to partition. So this is what this algorithm will do. Okay, but not only this will do, I say, hey, take this to partition and put it in my family. In the beginning, P is empty, and on that I'm dumping these objects. But now I will do some branching. What is my branching algorithm? This is what I'm teaching, right? In branching, because it's a branching algorithm. So now, here I have VC0, VI0, and A. Look. Now I pick a arbitrary vertex V in A. Okay? I pick an arbitrary vertex V in A. Maybe for some clique and independent set partition, this V is part of the clique. Right? I don't know this, but this V could be part of the clique. So first let's try to understand that V in A is part of some clique. Then what I say, okay, if this V is part of this clique, then you better go to VC0. Okay, so then I will go to the new state, let's call it delta V. What is this? And click. I mean, let me use the correct symbol, otherwise, okay, so let's not do this. V goes to C. Now notice, if this is the case, then all its non-neighbors, where should it go? To I. Its non-neighbors cannot be part of VC0. This much I know for sure. If I decide to put a particular vertex inside the clique, then its all non-neighbors cannot belong to him, right? So what will I do? Vi0, what will I add? Union A intersection non-neighbors of V, right? Or rather, look, if I decide to put V in the clique, right, the only set of people who could go to clique are vertices which are in the neighbors, which are neighbor of, right? So maybe the best way to do is I keep only those vertices which are active, which is A intersection neighborhood of V, okay? These are the only possible vertices which can go actually to the clique side, right? His neighbors. So then I put union here A minus Ng of V. If I decide to put this, so I branch. Maybe I decide to put delta V to independent set. Then what happens? If I decide to put a vertex into the independent set, then clearly all its neighbors cannot be here, right? And only people I can put here are his non-neighbors.
In the first state, if there are non-neighbors in this VC0 already, then we discuss them.
What?
Like it might be possible that there are non-neighbors in this VC0 already.
Let's not go. I mean, let's not go. I mean, maybe. I mean, let's not have a discard. Look, let's not go to the specialization case. This is, I'll just branch in all brute force way, and I'll show to you that one guy will take care of it. Look, maybe I'm outputting some irredundant partition, so be it. Right? Rather than trying to find a simplification rule for everything, I mean, yes, you're right, you can discard this partition. You shouldn't be branching on that. But it doesn't matter. I mean,
Because for every click, we know that it's a subset of it, it's not whole of it.
yes. Maybe for some other clique this guy is being taken care of, so we shouldn't be, okay? But for now, suppose I decide to put V into I, so what happens here? So what should I put here? So it should be A intersection, because that's only active vertex, B, right? And what is left then? A minus Ng of V. Okay? This is what I do. Okay? Lot of things are not clear. First of all, and I will stop when D is roughly 2 log n plus 1. And what is the branching here? Look, I do it for every vertex V. So I output a partition and I branch into 2n ways. Like for every V in A, I decide I create this. and I call my recursively, right? So what will the procedure will be for all v in A, okay, for all v in A, I have to generate, right? So I will generate G D plus 1, okay, and delta V goes to C, and then same here G D plus 1 delta V goes to I, right? So notice this is a two-in-way branching, right? And whatever, and look, D is increasing, right? And I will say, I mean, I don't know what to set here. Okay, so I will say here, if D is less than equal to 2 log n plus 1, then only you go to this code. So clearly I have just truncated this algorithm at 2 log n plus 1, right? Otherwise I don't go, like just output whatever, and in the beginning your P is empty, and each time what you do, when you have a delta, first thing you do is make these two things, put it to your family. This is exactly what you do. What you do, when you given a state, you first put this, what did I tell you? Okay, yeah, so this add to P. So this is what you do first thing. So okay, so now if I really have to write the code, so given a state delta, what is the first thing do? I make this thing, put it to P, where delta is some VC0, VI0, A. Okay, given this, I create two partition, put it to my family, and if D is less than this, for every V and E, I create new set of this and I keep looping this, right? Clearly, the number of objects which we will ever generate is, what is a branching vector? 2n. And what is the depth of this tree? Up to D, which is 2 log n plus 1. So clearly number of objects which it will create is n to the power big of log n. Now why this will do our job is not clear, but this definitely will do n to the power log n. Right? We have truncated. Now first let's try to prove that if we would not have done this truncation, then this procedure will definitely output the family which we desired. Okay. So let me define the notion of admissibility. Okay. Okay. We say that a state delta is promising. Okay, a state delta is promising if the some following things are satisfied. If so, what is delta? If you recall, it is x0c, xi0, and some a. This is how any state looks like. Okay, I'm going to call this promising if xc is a subset of x okay, no. So first you fix some click and some independent set. Okay, so you fix a click and independent set. I have to say that there is a partition where this is completely contained inside something, and this is what my job is, right? To show correctness, you give me a click, give me an independent set. So maybe I have just written xc and xi as that click and independent set which you have in mind. Now with respect to that, I'm going to define, we say that a state delta is promising for, I think, for xc comma xi if xc is a subset of what? xc0 union A, and xi is a subset of what am I writing? This will be confusing for you people. It will confuse me itself. Right? This is it. Agreed? I mean, what this tells you that look, this state is promising means I still have ways to extend this. So like I have still not violated anything, because any delta is a partition of vertex set. And what I'm saying at this point of time, look at my click. Oh, click, some vertex already is in the click side or the remaining guy is in A. Look at my independent set guy. I mean, whatever I have already decided, they are in distinct places. This is all that it is saying. There could be fix an I, either the vertices of I is in I or in the active vertices. It is not that it has gone to the click side. This is what it says, right? Look at any vertices of your independent set which you have in head. Either that belongs to the independent set partition or it is still active. Look at the click vertices. Either it is still in the click side or in the active side. It is not that this has gone to VI. Right? Otherwise, this cannot lead to a good partition. And clearly, for any XC, XI, empty set, and VG is a promising state. For any, this is a promising state because okay. So suppose I am in a promising state. Now I have to show that at least one of the branch you are moving in a promising state. Right? Do you get my point? Okay. So now suppose I have VC 0, VI 0 and A is a promising state for some XC, some XI. It could be currently this is a promising state. Now what could happen? What is XCA? It is my click intersection A. What happens if XCA equal to phi? It's a promising state, right? Then I have outputted this. If XCA is phi, it means all the click vertices is already part of my VC0. So then if I put everything else of A in I have got the valid partition. So this is happening. Similarly, if XIA equal to empty, right, it means all the independent set vertices is already in Vi0. Then I should just put A in VC0 and I would have got. And this is why this partition is okay. Okay. So now we are in the case when this and this, like at least one of them is non-empty. Okay. So if either of this would have been true, then we would have been good, right? If either this is true or this, then we would have got our partition, right? Because it is a promising state. So now what we know, XCA is not equal to empty, XIA is not equal to empty state. Now how do we handle this? Okay. Now notice here, let's come back to here. So you fix some V in XCA, some V in XCA, right? Some V in XCA because it is non-empty, so there exists a V. Now zero, right? And what did you add independent set guy? All his neighbors, right? Sorry, all his non-neighbors, right? So independent set, if it all can exist, can only exist in, so suppose this was my promising state, right? Now if I have a V in XCA and look at this state, I call that this is a promising state. For what? For which one this is a promising state? Now for this click XC, XI is still this is a promising state. Okay, my claim is then delta V to C is a promising state for XC, XI. This is what my claim is. Do you get my point? Why it is a promising state? Look, to show the promising state, we have to show that the XC is subset of VC0 union V union A intersection NGV. Okay, if V is in XCA, then where is the click? It's in the neighborhood of V, no? So some neighbors of V was already here and some neighbors of V were here, otherwise it would not have been a promising state for this click, right? And I have not removed his neighborhood from here. Now look at independent set. It was a promising for Xi. So what is the meaning of it was promising for this? Independent set vertices are either contained and what did I wrote? Look at Xi is a subset of Vi 0 union A minus NGV, right? Look at your independent set, right? Look at your independent set. Okay, is this a promising state for this? Can I say that my Xi is a subset of this? Look at only difference, but also its neighborhood, right?
No, but we have added. Talking about a fixed partition, no? That's why we can say. So then we can say, because if we look at this particular XC and this particular XI.
Yes, and we are talking only this particular.
Then look at how.
Look at Xi.
Exactly.
Look at Xi. Some vertices of Xi were already. What did I add to here? I added A minus NGV to this.
Which is same as non-neighbors of V.
Yes.
So non-neighbors of V in A.
Non-neighbors of V in A. But why can a neighbor of V not be part of independent set? Huh?
You add in the independent, because if V is in the clique, if you add non-neighbor also, then in XC this edge is missing, so this cannot be a clique.
Right.
But they are still active, right? The neighbors of. So they can be in the future.
Oh, right.
But we are talking.
Right. You're right. I was just by mistake I was looking at this and this was confusing me. Okay. Here it is, right? So what I have left here, look, neighborhood of V, right? Clearly, non-neighbors of V cannot be part of this. So that I have definitely moved. But the neighbors of V could either go to the clique or it could go to the independent set, and which is still here, right? But its non-neighbor will definitely not go to this side. So this is okay. So I was looking at this and I was looking at this. I said, what have I done in my life? Okay. So this is an active state. Okay. So now what does it tells you? That every time you branch, you are still going from an active state to an active state, and things happen. So if I would have just made this algorithm run till eternity and not stopped it, this definitely would have given me the going from an active, like I am going from a promising partition to promising partition, and every time I am doing some movement, at least like what is happening, at least XC intersection A is increasing, right? Something is happening, right? So definitely maybe at after n, right, I will do this, but I actually have stopped this guy at 2 log n step. So I must prove something non-trivial to say that hey, you would be done by this. Okay, do you get my point? Look, this algorithm, if I let it run to eternity, it is perfectly valid, right? But I stop this algorithm at some arbitrary, said okay, this is done. Why this is correct? Right? I have told you algorithm, right? I have told you why this algorithm is correct, right? Like you can prove using induction, right? What is base case is this, and now like on the level of the tree, base case is oh this is fine for up to level this, so I want to prove this, so this is down, so this will lead to a promising state, right? And this would have taken care of if something happens here, and then okay, good. Okay, so what should I rub? You got this. So let me rub this algorithm.
For this login, it will be like amongst the click and independent set in A, one of them must have more than n by 2. So when we are selecting this, it will become n by 2, n by 4, and then like this.
I mean, whenever you see login, that doesn't mean that that's all that it happens. It's an unfortunate part of the world. You need more. Like you said this. Why did you say this? Let's go back to that. Like substantiate.
Because I'm saying A has the remaining vertices of XA and XI, but amongst that, if there is A, one of them must contain more than A by 2. Like, because A must, like part of A we are going to put in VC, the remaining part we want to put to VA. But then greater than half of this must be in one thing, right? Greater than.
You ask your friends if they're convinced.
Given in XC, XI.
Okay, so should we try to write what is he trying to say? So what are you saying? Okay, what are you saying? Okay, tell me. Okay, so what are you saying?
So what I'm telling is now you're given some XC and XI.
That is fixed.
You're fixing some XC and XI.
Fixed.
I'm telling that amongst this from A, right? Like leaving the vertices in VC naught and VC.
So and we have some delta. Okay, which is VC0. I don't know why I'm writing this, but and A. What are you saying now?
Yeah, so what I'm trying to say is now either XCA will be greater than XIA or XI
What you're saying? XCA.
will be greater than XIA or greater than
XCA is greater than equal to.
XIA or it is the other way.
Okay, fine.
Okay, so for all these partitions, this is so given any partition.
Yeah, this is like by pigeonhole principle. Either this is big or this is big.
Yeah.
So now what you want to say?
So what I'm trying to say is now in the first case when XCA is greater, this promising state, choosing the first promising state will kind of, so when you're taking the neighborhood of that, it will decrease more n by 2.
But why?
Because that is greater than equal to A by 2. One of them must be greater.
What? Look, XCA is some set of neighbors. XIA is some set of neighbors. You're talking about set.
And it has to work for every XC, XI, not just one fixed XC.
C and fixed XI. It has to be true about every XC and every XI. Okay. So it requires more clever argument. Okay. Here I have XCA. Here I have XCI. Let's look at all the edges in the graph between them. Okay, edges. Let this edge be F. Okay. Edges between XCA and what am I writing?
XI.
Okay. Suppose cardinality of F, number of edges, is more than what can you say? So there are more edges here than non-edges. This is what it represents, no? Like between these two parts, this means there are more edges than the non-edges. More edges than non-edges. What can you say now? Can I say something? There exists some vertex which sees half the guys here. There exists some vertex here which sees half the guys here. Because everybody if saw less than half, it's a bipartite graph, this inequality wouldn't hold. Means there exists a V just by appraising argument such that what happens? Neighborhood of V, what was XCA? Neighborhood of V intersection A is greater than equal to what? Neighborhood of V intersection XCA strictly greater than equal to CA by 2. So what happens because of that? Suppose if I find this, look, not all steps, look, I have just terminated, but I know in some step I am making lots and lots of progress. So pick up that particular V. Look, I have proved that you've given me any XC and XI, like there is in the beginning if I have promising state, I have at a promised state, then there is some vertex, and look, my loop was for all V. For that what happens if I branch? What do I find? So if I put this V in I, then what happens?
The A size decreases.
You have put, what do you do? A intersection NG of V is put here. So look at that XC, do not look at N or something. The click side, the remaining vertices of the click side, you have put half the vertices of that click side into your VC0. This is what you do, not anything else. If I branch on that V, what I am doing? Look, what is XCA? The remaining vertices, the vertices in A which has still not been decided where to go. But by deciding to put V in him, all his neighbors I have put it in the click side. It means in particular I have, so this is XCA, so maybe I am putting more things, but definitely for this XC I have at least put half the vertices to this side. So for this particular click I have made progress. Agreed? Okay. So you have to be a bit, it is a bit, or okay, this I can now. If this does not happen, then what happens? If this does not happen, then what happens? Number of non-edges is less than equal to XCA times XIA divided by 2. So there are more non-edges than edges. What can you see?
In this case, in that too.
Then there exists a vertex V where? Here in XCA who doesn't see at least half of them, right? Which does not see at least half of XIA, right? Okay, V such that at least XIA divided by 2 vertices are non-neighbors of V. Then what happens? Let's look at this. Then in this case, when I branch into this, what would I have done? So if I decide to put this guy here, all his non-neighbors I put it here, right? So in particular, I have reduced the size of xia, the remaining guy of the independent set, by half by doing this, right? So there is a path for every xi xa which will not be more than 2 log n. And why 2 log n? Because in one step either I decrease xc size by half or I decrease xa size by half, right? So this is why you are looking at 2 log n path, okay? And now how do you argue? In general, hey, in the beginning for any xca and xia is empty, alright? How many edges? No. In the beginning, what is xca? Is whole of a click and whole of independent. How many edges can there be? N square, right? So the measure of this will decrease, like, so this is why this step will go 2 log n. But the other way of looking at it, at any step, either xc decreases by half or xa decreases by half. And every time where heat decreases, that's a promising state. So if I cut down at 2 log n, maybe not all partitions are great for me, but for every click and independent set, there is a good partition which does this job for me. Am I right? Okay. So this is also a branching algorithm. Okay, and this is an amazing branching algorithm because what does it tells you? It tells you a extremely amazing, powerful separating family, right? That you give me a click and you give me an independent set, right? And I will give you a partition of vertex set that your click and independent set are separated from each other, right? And how many such partitions are there? Only quasi-polynomial, okay? So there are lots of conjectures in communication complexity, LP, and all are related to each other. So now imagine I'm Alice and I'm Bob, okay? I'm Alice, okay, C is Alice, you are Bob, okay? I cannot be Alice, but maybe I'm Alice, it's fine. And you have given a graph G which both of you can see. And you have a click, he has an independent set, okay? And they want to test whether, what do you call, whether it is disjoint or not by communicating as few number of bits. So everybody can see the graph, but he cannot see your independent set and you cannot see his click. So they pre-agree on this partition, right? They pre-agree on this partition. And this is a deterministic protocol. So they pre-agree on this partition and they say, look, here is a partition, right? So what I know by looking at this partition, as a Bob, you say, so she is sending me this partition, it means her click is completely contained inside this. Look, both of you point to the same guy, right? Both of you just point to the, like, so how will you do this? You say, look at the, just canonically, like lexicographically order them. Look at the first guy which separates your click and independent set. Look at the lexicographically first partition that separates your click and independent, and that's unique. Because, and this ordering both of us already have pre-decided. Like I know partitions and everything. So what all things I need to tell you? I need to tell you, hey, here is a partition, right? You also point out to the same partition. Then what is the meaning of this? Your click and independent set will be distinct. Otherwise, if you point to different objects, then it is not. But how many bits of information do I pass? Log square n bit. Because there are n to the power log n. So to tell you in coding, like which partition my click is or my independent set is, I need log of n to the power log n, which is log square n. Right? So this is where it comes. And the question was, can we reduce this deterministically? And they proved that some log n to the power 4 by 3 or something can be done, and that's optimal. And in randomized way, you can do log n. You just give one vertex or something. I forgot now. Okay. So this is from where this comes. So to show that to give a deterministic protocol, people came up with this separating family. Okay. So it's 12.